Now that we can interpret at least the directionality as well as the substantive effect size, right? So a unit change in x is equal to this beta change in the, remember, odds ratio of having CHD. Now we want to know whether or not that relationship, that beta relationship, that one unit change is actually a statistically reliable change, right? So what we're trying to do here is run a hypothesis test for our various betas. Now, in this case, since we're using a single covariate, we're probably only really substantively going to be interested in beta 1, but this is just a general rule of practice, right? So remember that estimating these beta j's, they are going to be asymptotically normal, which is nice because basically what you're doing now is just using a z-test or a wall test for your covariate significant test, and you know exactly how to do this. This is pretty much the exact same as any of the other linear regression models that we've been using, right? Where our null hypothesis is that there is no relationship, and the alternate, right, is that there is a relationship. To construct that z score, our test statistic, right, we're interested in the difference between the estimated coefficient and what we think that coefficient is. So that's just beta j minus 0. So that's why we just have the beta j here. And that's over the standard error of the estimated coefficient, right? So if we get a p-value that's less than our critical threshold, we're going to go with 0.05 like usual. Then we can conclude that the predictor is a statistically reliable predictor of CHD in this instance, right? And we're going to calculate a confidence interval around our beta in the exact same way, where at the center we have our beta estimate, and that's plus our z statistic, right, multiplied by that standard error. Now, looking back at our estimated coefficients from our regression model, I've kind of already cheated and put this up here just to show you, but we can clearly see, right, just like as a general rule of thumb, the standard error should be about half of the estimated coefficient, and in both cases, these are statistically reliable. This is really the one that we care about, right? So here we'd say that the effect of age on someone's propensity to have CHD is positive and reliable in the sense that as someone ages, the relationship between increasing age and increasing CHD is statistically reliable. Now, just like with linear regression in OLS, we can test whether or not several of the coefficients are statistically reliable. So here we're setting up an f-test, right? Where we're saying, is any beta coefficient reliable? Is there any relationship among any of the predictors that we've included? And we go about doing this in the exact same way, where we're comparing the likelihood of each model and seeing whether or not we think the differences in the likelihood or the model fit of each of the models is differentiable from each other. We do this using ANOVA, where we have the reduced model. So this would be basically our y with just an intercept. This would be our full model, so all of our covariates, right? And we're running a chi-square test. Again, if the value is less than our critical threshold of 0.05, then we would conclude that at least one of our predictors, so we weren't, but you could think of including age, exercising, maybe even whether or not people are smokers, those are all potential covariates. And so in a model where we have a full model, we'd be comparing that versus one in which we have no covariates.